CPU, Central Processing Unit. By the end, a chip that does in 5 minutes what a supercomputer couldn't finish before the universe ends. But it starts in your pocket. There's a chip in every computer on the planet. Has been since 1971. And almost nobody can explain what it does without a half-believed metaphor. Here's what breaks most people's model. It isn't one brain. It's a whole building of them. It's the ultimate generalist. Opening a browser, running a spreadsheet, checking if your mouse moved, all of it, sequentially, at impossible speeds. 3 to 5 gigahertz. Billions of operations a second, on a chip the size of a fingernail. And it runs 4 to 24 cores. Each its own task. Your music, your browser, your virus scan, all at once, not taking turns. Intel, AMD, and Apple build them differently. The idea hasn't changed in 50 years. The honest limit? It's terrible at doing one small task a million times in parallel. Ask it to render a full 4K frame at once, and it falls apart, which is exactly what the next chip was built to solve. GPU, Graphics Processing Unit, built for video games. That part is true. What nobody predicted is that it would become the engine of the entire AI revolution. Whereas CPU has 16 powerful cores, a GPU has thousands of simpler ones. NVIDIA's RTX 5090 packs over 21,000. The hiring analogy: a CPU is one brilliant generalist. A GPU is a warehouse of interns who each know one thing. If the task is filling 8 million identical envelopes, the interns finish before lunch. Rendering pixels is filling envelopes. Training a neural network is 2 millions of identical matrix multiplications running simultaneously. The insider reframe: ChatGPT, Midjourney, Stable Diffusion. None of them run on CPUs. NVIDIA's market cap crossed $3 trillion because the world quietly needed 1 million of their chips for a use case nobody anticipated when designing graphics cards for Counter-Strike. The limit is power. An RTX 5090 pulls 575 watts, a microwave running continuously. Someone looked at that and asked, what if we built a chip that only does AI math and nothing else? TPU, Tensor Processing Unit. Google's answer: released 2016. No press event, just a paper saying, we built a chip for neural networks and it's faster per operation than anything on Earth. Neural networks are endless matrix multiplications. A GPU was built for something similar. The TPU was built for exactly this and nothing else. The analogy: a NASCAR car can only turn left. On a road, useless. On an oval, it beats every Ferrari. You can't buy one. You rent time on it through Google Cloud. Total inflexibility is the trade-off. But for the one lane it runs in, nothing comes close. For everything outside that lane, a different approach was needed. One that fits in your pocket. NPU, Neural Processing Unit. Your phone has been doing AI for years. You just didn't know what was handling it. Apple embedded the first serious NPU in the iPhone X in 2017. Now every Copilot plus PC must include one capable of 40 plus TOPS. Trillions of operations per second just to earn the label. It's why Face Unlock happens in 200 milliseconds. Why background blur runs in real time. Why voice transcription works offline. When your iPhone edits a photo instantly, you probably assume the CPU did it. It didn't. The NPU did, silently, on a battery budget measured in milliwatts, not megawatts. The honest limit: it can't train a model. It only runs them. A specialist at the end of the pipeline, not the beginning. The NPU solved the mobile problem, but there's a different bottleneck. One that lives in the gap between how language models generate text and what GPUs were built to do. LPU, Language Processing Unit. Most people in tech still haven't heard of this one. Grok, not Elon's Grok, the chip company with a Q, built the LPU to run language models at speeds that felt like cheating. 500 plus tokens per second on Llama 3. A GPU cluster doing the same task might produce 50. That's not a modest improvement. That's a different category. The architecture insight. Language models are sequential. Token by token, each output depends on the previous one. GPUs are built for parallel work. Running a language model on a GPU is like hiring a warehouse of interns to write a single sentence. Most of them wait while one works. If you've seen Grok's demo and watched text fill the screen faster than you can read, that's not a trick. That's the LPU. Narrow scope is the trade-off. No training, no graphics. One lane, extraordinarily fast. DPU, Data Processing Unit. Nobody talks about this chip. It keeps the internet running anyway. Networking, encryption, storage traffic, security checks, all the infrastructure grunt work that keeps a server talking to the outside world. The DPU handles it so the CPU and GPU don't have to. Think of it as the logistics team in a factory. Nobody in the showroom sees them. The factory floor stops without them. If you've ever used AWS, Azure, or Google Cloud, a DPU handled your packet. Invisible. Load-bearing. Everywhere. FPGA. Field Programmable Gate Array. Every chip on this list is fixed at the factory. Same architecture forever. An FPGA isn't. It's hardware you can reprogram after manufacturing, after deployment, after the product ships. Load a new configuration file. Same physical chip, different function. Networking accelerator on Monday. Signal processor on Tuesday. That's why FPGAs run inside 5G base stations, medical imaging equipment, and financial trading infrastructure. Anywhere someone needs hardware-level speed but can't commit to a single fixed design. The honest trade-off, they're the hardest chip on this list to work with. You're not writing software. You're designing hardware in code. High ceiling, slow cycle, QPU, Quantum Processing Unit. Everything above runs on the same logic. Bits, 0 or 1. No third option. A QPU uses qubits, which can be 0, 1, or both simultaneously, through a property called superposition. A classical computer checks answers one at a time. A quantum computer explores all of them at once. Google's Willow chip solved a benchmark problem in under 5 minutes that would take the fastest supercomputer on Earth 10 septillion years. Longer than the age of the universe. That already happened. The honest limit. Cooled to minus 273 degrees Celsius. Chandelier-sized. Useless for Chrome, email, or anything daily. And right now, errors accumulate faster than quantum systems can correct them.